In this video we want to look at section 8.4 of Young and Freedman's University Physics, which is on elastic collisions. An elastic collision is one in which the kinetic energy is maintained both before and after the collision. So two pool balls come together and separate, and there's no appreciable loss of kinetic energy before or after the collision. Of course, I suppose technically there is no such thing, but we're talking on a macro level, and on a macro level, a hockey puck and these sorts of things, for most usual purposes, we're going to go ahead and say that the collision is elastic. So this section is about finding the resultant velocities and directions of two bodies after an elastic collision has taken place. It starts, and the majority of this section is about collisions in one dimension, say on an x coordinate line. That's to keep it simple, and then of course you can branch out into other dimensions, 2 and 3 dimensions, later on. If you understand the collision in one dimension, then by extension you can understand collisions in 2 and 3 dimensions. The final example of this section has to do with a collision in 2 dimensions. Now, just a little reminder of math that helps understand what they do in this section. In general, you need as many distinct equations as you have variables to solve. Now, I just came up with this idea of info equations. That is, what I mean is equations that describe the situation that you're trying to analyze. So you have a situation. Let's say you have more than one unknown. Let's say you're working with a velocity 1 and a velocity 2. So you have two unknowns, two different velocities you're trying to solve for. Well, then you're going to have at least 2 equations in relation to that situation, say that collision, in order to be able to solve for 2 variables. In general, you need as many equations as you want to solve for variables. So if you're solving for 2 variables, you're going to need 2 equations relating to the situation you're trying to analyze. If you're solving for 3 unknowns, so the last example is in 2 dimensions. So you're not only solving for an initial velocity in that example, but you're also solving for an x and a y coordinate of the resulting velocity. So if you have 3 unknowns, you'll need 3 equations. If you have 4 unknowns, you need 4 equations relating to a situation in order to solve for all the unknowns, for all the variables. So that's a little math reminder that comes in handy in this chapter. So if you're solving for velocity 1 and velocity 2, that is the velocity before a collision and the velocity after a collision, then you're going to need at least 2 equations that describe the situation. The first equation that he uses is the kinetic energy equation. Ke stands for kinetic energy. So kinetic energy equals 1/2 mv squared. So this is a collision we're looking at here. So mass A moving at velocity A, 1, that's the initial one, and mass B with velocity B, 1, before the collision. So this is 2 bodies with 2 masses, body A, body B, that collide with each other before the collision. Each of them has a velocity. That kinetic energy before, since it's an elastic collision, remember from the previous section, in an inelastic collision the kinetic energy is not conserved. But since we're talking about an elastic collision, it's going to be conserved. That means that the kinetic energy after the collision is going to be the same. So 1/2 mass A and its second velocity squared plus 1/2 mass B and its second velocity squared. It's going to be conserved. So we have one equation. Now we're assuming that we know the masses. All of these exercises assume we know the masses. So MA is known, MB is known. And in many of the examples in this chapter, the second body is at rest in the example. So VB1 is known in most of the examples. The other equation that we can work with is the momentum equation, where P stands for momentum. So mv of A before plus mv of B before equals mv of A after plus mv of B after. So that's conservation of momentum, which applies in this situation. So we have 2 equations, And if we're solving for V1 and V2, then we have two variables. Actually, a lot of times, the V1 and V2 is probably not helpful. The final velocities is usually what he's solving for. So VA2 and VB2 are the two unknowns that he's solving for in the first two examples. Okay. Some conclusions he reaches early on. He works some examples, or they work some examples, where the second body is at rest initially. And what he finds is that if one of the options in the collision is at rest and has a much greater mass than the body coming toward it, like if you put a ping pong against a bowling ball, then the first object will bounce back in the direction it came with a similar speed. So if you roll a ping pong at a bowling ball, the ping pong is largely just going to bounce back in the same direction it came from, with only a slightly less speed. The bowling ball is only going to move slightly. On the other hand, if the mass of both of these objects is equal, and the second body is at rest, then the first one will stop and convey all of its kinetic energy to the second one, which will continue at the initial velocity. You know this if you've ever played pool. You know, if the cue ball hits, one of the other balls straight on a line, the cue ball will stop completely, and the other ball will continue moving at the velocity that the cue ball had. These are some things that he shows mathematically why that the math proves it or demonstrates it in some of the examples he starts off with. Also, another conclusion he gets is that in a straight line collision, the relative velocity after the collision is going to be of the same magnitude but the opposite in direction after the collision. So if you take the initial velocities, and it doesn't matter whether the second body is at rest or not with this one. If you have two in a straight line collision, the resultant velocity, the difference between the two velocities before and the difference between the two velocities after is going to be exactly the same in magnitude. It's just going to be negative. It's going to be in the opposite direction. So those are some conclusions that he reaches just by taking the formulas that we, and playing out different situations. And that's all stuff that you've observed if you've played pool or with a hockey puck. Now, he ends the final example with more than one dimension. Two pucks on a table where it's not a straight-on collision. So to know the resultant velocities is going to require at least three different equations to describe that situation if we're going to be able to tell how it ends up. And the three equations he uses are, again, conservation of energy, so that one's still going to hold. Kinetic energy before and kinetic energy after, again, is going to be exactly the same. But he also then uses the conservation of x momentum and the conservation of y momentum. So that makes three equations, so he can solve for three unknowns. In the straight line collision, he just used conservation of x momentum, as it were. And now that we have two dimensions, he uses conservation of x, y momentum. And so he can solve for the x momentum, and he can solve for the y momentum, or he can solve for the x velocity, and he can solve for the y velocity, and that creates a situation where trigonometrically he can find the angle at which the puck goes off to the side. So that's basically section 8.4 of on elastic collisions.